Abbas. Abbas, do you hear me? Mr. Abbas. Salam, salam. Where are your friends? I tapped in the Telegram, but anyone came in here? You are lonely, and other students isn't in the class. That's right. We start for others coming. Okay. We was in discussing, for example, firstly, it was here at first Wash transform, and then Hadamard transform, okay, and ordered Hadamard transform, and it was here for depicting some good features of ordered Hadamard transform. That's right. In this slide, demonstrate and compare the energy compaction property of DCT and ordered Hadamard transform. Okay. Review of the last session. Consider an image of size n by n. The pixel 00 is located at the top left corner. Calculate the density of the image. What are you typing? Okay, in this tutorial we said that for example, here for example is the original image, and this is the DCT, okay, the DC transform of that image, and we have a parameter EI. Internet ضعيف. Okay, actually they're coming, and this is EI. EI is the energy of image, okay, using this parameter I. I is the number of, for example, n by n or I by I, okay, the number of pixels in the transferred version. You see, with salam Mr. Yasser, salam. Oh, some of you are coming in the class, but with some larger delays, okay? Mr. Abbas, Mr. Dalal, and Mr. Yasser. Salam. So high delays. Mr. Dalal, Mr. Yasser, and Mr. Hamid. About 1 quarter. That's right. We saw a small item of the transformed image can transfer to us a high energy of the image, okay, and this is a very good property for comparison, okay. That's right, or compaction. Go to the next slide. Another one, demonstrate the energy compaction property of density and ordered Hadamard transform, okay. Obviously EI is a molecularly increasing function. You see here, EI is increasing by increasing I, okay, molecularly increasing. We can call it cumulative energy function, okay, as CDF versus PDF, cumulative. I increased, I is increased. Salam, Mrs. Lome, salam. For fixed I, the percentage of energy contained in the DCT patch is higher than the percentage of energy contained in the Hadamard patch. Okay, we saw in the last slide here the red compared to the black one. Okay, red is for DCT, but black is for Hadamard. Okay, ordered Hadamard. We see here that DCT is better. DCT is better. A higher percentage of EI, okay, compared to ICE. But DCT calculation is more complex than Hadamard calculation. Okay, here. For a fixed I, the percentage of energy contained in the DCT patch is higher than the percentage of energy contained in the Hadamard patch. Observe that the DCT curve is located slightly, no very huge difference, slightly above the Hadamard curve. That means both of them are the same, okay, near each other. But computing Hadamard is very fast, or more fast than DCT computing, okay. Or in order to keep a fixed percentage of the total energy of the image, you require a smaller patch when you use DCT compared to the one you require if you use Hadamard. Okay, but we said Hadamard and DCT are the same. In the above experiments, above is this slide. Okay, in the above experiments, you observe that as I increases from 1 to slightly higher values, the fraction of the total energy EI becomes almost 1 quite quickly. You see here, for example, we said, for example, from 256 components, you can use only about 20 or 40 components, okay, and almost you reach more than 90% of energy, okay, near total of energy, okay. In other words, the preserved patch contains almost total of energy, okay, total energy of DCT image. Don't forget that the energy preservation property, both space and transform space have identical energies. This is the Parcel Theorem. The energy in the, for example, X or Y domain is the energy in the U or V domain. Okay, this is Parcel energy theorem. That's right. Go to the next slide. Again, the observation in the previous two slides rely on the fact that both DCT and ordered Hadamard transforms exhibit the property of energy compaction. Okay, these two transforms are very good for compression or compaction of energy. Okay, because using a small value of I, you can reach almost all of energy, okay, or all of information, almost. This is compaction or compression. That means ordered Hadamard and DCT are good. When we repeat the experiment for the non-ordered Hadamard transform, this was for ordered Hadamard, okay. When repeat for non-ordered Hadamard transform, we observe that the cumulative energy function does not increase quickly, okay, towards its maximum value. Not as good as ordered one. On the contrary, it looks more or less like the straight line type of function with moderate slope. Okay, we see in the next slide. To verify this observation, look at the next slide. Okay, here. This is the ordered Hadamard. This is the non-ordered Hadamard transform. Okay, for the same picture, cameraman. This is ordered one, and this is non-ordered. And here, EAI, cumulative function energy. Okay, you see here, this one is for ordered EAI, ordered Hadamard transform, and this EAI, Salam Zainab, and this EAI is for non-ordered Hadamard transform. Okay, and Salam Dena. Okay, you see that the ordered one is very better. It's very better. Why? Because this is fluctuating, and a large number of EI is, for example, here, a large number of I is required to reaching a good EI. But in the ordered transform, with using a small EI, for example, here, you can reach almost the total of energy. Abstractly, ordered Hadamard is very good. Ordered Hadamard is less than DCT, but ordered Hadamard computing is very simple and very fast and is very good transform. Okay, this is the last slide for the DCT, for Walsh transform, and for Hadamard transform, and ordered version of them. Okay, and I stop sharing and go for the last Salam Mr. Yasser, and go for the last transform, and then close this part of the lecture. Okay, I stop this one. I upload another transform named KLT. Crown and Lave transform. This is the last one. We had DFT. This here, Salam Ahmed. Salam. طاعتكم مقبول كلكم. رمضان مبارك كلكم. We had DFT, discrete Fourier transform. Then we had DCT, discrete cosine transform. Then we had DWT, discrete Walsh transform. Then we had DWT, DHT, discrete Hadamard transform, and we saw the ordered versions, ordered Walsh and ordered Hadamard transform, and abstractly we saw that from all of them, ordered Hadamard is a good version. Okay, ordered Hadamard transform, and maybe better than DCT because of its good properties. Okay, H2N was reconstructing from HN. Salam, Mrs. Maryam. And after all of them, we are here for KLT. Okay, Crown and Lave transform. And after this lecture, we go for the next items of the class. Okay, and the transforms is completed. Okay, this is the last transform. That's right. Digital processing, image transforms, DFT, DCT, DWT, DHT, and here KLT, Chronology Transform. Okay. But this item. But first of all, we should say about agent values, agent functions for understanding KLT. Okay. In this lecture, we will introduce a new transform and the last transform, so-called Chronology Transform or KLT. Okay. And KLT is as the last transforms. Okay. Unitary transforms for going, for example, from X of Y domain to the spectra domain, from a spatial domain to a spectral domain, or from X of Y to U of V. The concepts of agent values and agent vectors are important, or are very important, for understanding the principles of KLT. Okay. For example, if C is a matrix of dimension n by n, okay, then a scalar lambda is called an agent value. Agent value of C if there is a non-zero vector E in Rn such that CE is lambda E. Okay, this is definition of agent values. Okay, maybe you had agent values in your undergraduates, maybe in calculations. Okay. Or maybe in other, for example, here in Iran, we have agent functions and agent values in equations, in numeric calculations, in, for example, for or field in electrical circuits, etc. On in mathematical engineering, okay, or engineering mathematics, agent values and agent functions. But by definition, where we had CE is lambda E, okay, we say to E as agent function and lambda as agent value. Oh no, to E as agent vector or agent and to lambda as agent value. Okay, the vector E is called an agent vector of matrix C to corresponding to the agent value of lambda. Lambda is an agent value and E is an agent vector of matrix C when CE was lambda E. This is the definition. And maybe you had it in undergraduate, okay, in your mathematics. You had it or not? All of you. Are you familiar with agent values and agent vectors or agent functions in your undergraduate? Mr. Abbas, Mr. Ahmad, Mrs. Dalam, Mrs. Danam, Mr. Ahmed, and all of you. Mrs. Lom, Mrs. Sarah, Mr. Yasser, Mr. Yasser, Mrs. Zainab, Miss Mariam. Oh, okay. I said, was you familiar with agent vectors and agent values or not? No, there isn't Huzur Ghiyab. I asked a question. That's right. Another one. After defining agent values and agent vectors, defining or definition of a population of vectors. Okay. Consider a population of random vectors of the following form. Salam Mr. Uday. Ahlan wa salam bil ta'khir. More than half of an hour. Where are you, Mr. Uday? Okay. A population of random vectors X. X is okay. Oh, that's right. X containing vectors x1, x2, xn. صوت غير واضح. I stop my camera. Maybe صوت is better. Please Maryam, صوت is better or not? صوت is better or not? I stopped my camera. Cool. Okay. That's right. Good. That's right. This time or when I shared my camera. Camera isn't required. Okay. That's right. The quality of xi, x1, x2, x3, etc. The quality and the quantity xi may represent the value of an image I. Okay. For example, gray level of image I. That means x1 for image 1, x2 for image 2, and etc. And x1 KOL. That means the gray level of all of pixels of image 1, and the gray level values of all of pixels, all pixels of image 2, and etc. Okay, these vectors are defining the intensity value of gray levels of some pictures, n pictures. Okay, this is the total of vector x. We have n images, x vector for some particular image. Okay, all of equal size m by n. All of them have the same size. Okay, each of the above vectors refers to the exact same location across the n images. Okay, for example, x IOJ and xy IOJ, x1 IOJ, x2 IOJ, and xn IOJ for pixel IOJ, for example. Okay, all of these vectors showing some gray level intensities for a 1 pixel in n images. Okay, therefore it's more accurate to write x KOL, x total KOL, as a vectors of x1 KOL, x2 KOL, and etc. Then k from 0 to all of m, okay, from 0 to m minus y1, and L for m by n size. Okay, k for m from 0 to m minus 1, and L for n dimension. Okay, or x of y dimensions. Go to here. Here's a good presentation. For example, derivative of previous scenario with n equal by 6. Okay, this is the image 1, is the image 2, image 3, etc. For example, 6 images. For example, a spectrum band 1, a spectrum band 2, to a spectrum band 6. This transform is for very good for, or is good, not very good, is good for multispectral image processing. Okay, and these are K and L, KL, okay, or X or Y dimensions, and each of them are pixels. For example, this pixel, this pixel, this pixel, this pixel in all of the images. That's right. Formation of a vector from corresponding pixels in 6 images. This pixel in image 1, this pixel, corresponding image, in pixel in image 2, this in image 3, and all of them. Okay. Go to next slide. Okay, here we have some description about mean of this population, or mean of x vector containing x1, x2, x3, etc. About mean of this m function, x function, or x vector. The mean vectors of the population are defined as m x KOL. M means mean, okay, or average. M x equal L is expected value of E, or expected value of x equal L, okay? Or is M1, M2, and Mn, okay? That means averaging vector 1, all pixels in vector 1, okay? Vector 2, or image 2, and to image n, all m by n pixels, okay? And in form of transpose or vertical vector, okay? This is calculating expected value of, or mean of the x vector. As you can see, we assume that the mean of each pixel KL or IOJ in each image I is different. That's right, because image 1 is different of image 2 and all other images, okay? Each of images have a specified average, okay? M1, M2, etc. In this case, we will require a large number of realizations of each image I in order to calculate the means MI KL. It's very hard calculations, okay? All of IOJs or all of KLs in all of images, okay? However, if we assume that each image signal is ergodic, maybe you are familiar with ergodic random variables, okay? Or maybe you are familiar with random processes, stationary and non-stationary random processes from random variables from random processes, okay? Ergodic random variables are good performing processes, okay? Good performing or good ones. If we assume that each image signal is ergodic, when we have some ergodic process, when or ergodic non-stationary variables, when, for example, the source are independent, okay? If probabilistically our sources was independent, we can by a good approximation say, or variable or random variable is an ergodic random variable, okay? If we assume that each image signal is ergodic, we can calculate a single mean value for all of pixels from a single realization or from a single image, okay? Or from a single image from a one spectral band, okay? Using the entire collection of pixels of this particular image. That means not requiring calculating the averages or means or expected values in all of the images. One image is enough if our variable was ergodic. That's right. In that case, MI equal L is MI, not requiring all of images, only in image I, for example image 2. That is 1 over m by n sigma all items of K, sigma all items of L, xi equal L from only image I, for example image 1, not all of images. That's right. I turn my camera on. If the quality of my sound was weak, please feedback to me. Okay, MAX, X is total of population, okay? MAX or MX equal L is MAX and is M1, M2 and MN transpose. That means if our process or our random variable was an ergodic one or ergodic variable, okay, M total is equal by M1, is equal by M2, is equal by Mn. averaging in one image is equal by averaging in other images. That's right, for an ergodic process. Go to the next slide. We said about mean. Here we said about covariance. Okay, covariance of this total vector of X. The covariance matrix of the population or X vector or population of vectors. For example, in that slide we had 6 vectors for 6 images. Okay, this is the meaning of population. The covariance matrix for this population is defined as CAX is expected value or mean of X minus by MAX or X minus by average dot X minus by MAX T. T means transpose. Okay, this is the meaning of or the definition of covariance matrix. Cx is of dimension n by n if all of them was n by n. Let's take a look. In probability theory and statistics, a covariance matrix, also known as dispersion matrix or variance covariance matrix, is a matrix whose element in the IOJ location or IOJ position is the covariance between the i's and j's elements of a random vector. Okay, we have variance and covariance. Okay, variance means the differences between for example i's and j's intensity level of an image or of an random vector. That's right. That's right. Because the covariance of the ith random variable with itself is simply that random variable's variance. Each element of the principal diagonal of the covariance matrix is the variance of one of the random variables. That means over the principal diagonal, okay, over the principal diagonal we have variance. Other items, okay, what is the principal diagonal? A1, A2, I, for example, 2, 2, 3, 3, etc. These are the components over the principal diagonal. Okay. What other items? IJ, 1, 2, 1, 3, 2, 5, etc. These elements contains for covariance. II consisting variance and IOJ consisting covariance. That's right. Every covariance matrix is symmetric and positive semi-definite, not positive semi-definite. Okay, positive semi-definite. Recall that for every symmetric matrix of dimension n by n, we can always find a set of n orthogonal eigenvectors. We said about eigenvectors and eigenvalues. Okay, if we had a symmetric matrix from the calculation principles, okay, we had in the, for example, undergraduate. If we had a symmetric matrix, we can or we had n eigenvectors, okay, for a matrix of n by n. Here, the KLT, Chronology Transform, okay, these two scientists have introduced a new transform named Chronology Transform or KLT. Based on that principles we said in the last slides, okay, based on eigenvalues, eigenvectors, symmetric matrices, mean and covariance, etc. Okay, let A be a matrix whose rows are formed from the eigenvectors of the covariance matrix CAX of the population of vectors X. That means we have some images, for example 6 images or 10 images, okay, and corresponding to each image we have x1, xi for image I, x2 for image 2, for example x10 for image 10, okay. Each of this xi, for example, is a two-dimensional vector matrix, okay, a two-dimensional matrix, xi, x2, x1, 2, etc. We have a population of these vectors named x, okay. X is for total of images, image 1, 2, 3, etc. And we have a covariance matrix CAX for this population of images, okay. We have a population vector X, and we have a CAX. CAX is the covariance of that X, okay. X is containing all of images information, x1, x2, x3 for image 1, image 2, image 3, etc. That's right. Let A be a matrix whose rows are formed from the eigenvectors of the covariance matrix CAX. We said about CAX. This CAX is a symmetric matrix, okay, and have some eigenvectors. For example, for n by n, have n eigenvectors, okay. What is A? A is a matrix whose rows, row 1, row 2, row 3, are that eigenvectors. Each eigenvector for one of the images, okay. E1 for image 1, E2 for image 2, etc. These images, these eigenvectors containing constructing the rows of A are eigenvectors for images 1, 2, 3, etc. Let A be a matrix whose rows are formed from the eigenvectors of the covariance matrix CAX of the population of vectors X. That's right. The eigenvectors are ordered so that the first row of A is the eigenvector corresponding to the largest eigenvalue of CAX, and the last row is the eigenvector corresponding to the smallest eigenvalue of CAX. That means A is containing row 1, row 2, row 3, etc. What is row 1? Row 1 is eigenvectors of, for example, image 1. Row 2 is eigenvectors from image 2, etc. Here we reorder, okay. We reorder the rows. How? So that the row 1 contains the largest eigenvector. Row 2 is the next eigenvector, okay, some smaller, and the last vector, last row contains the smallest eigenvector. That's right. Again, the eigenvectors are ordered or rearranged so that the first row of A is the eigenvector corresponding to the largest eigenvalue. Okay, each eigenvector has a eigenvalue corresponding to it. Okay, we reorder the rows or the eigenvectors so that the eigenvector with largest eigenvalue is in the first row, and the last row is containing the eigenvector with the smallest eigenvalue. That's right. Okay, we define the following transform as here. This is the transform of named KLT. Okay, this transform. Y y is a new vector, okay? Y is a dot x minus max, okay? Max was mean of population, okay? X was population of vectors, a was this eigenvectors that we said, eigenvectors of CAX, okay? Covariance matrix of vectors, is called the Chronology Transform. Y is a x minus max. And we see in the new slides some properties of this transform. Is it good or not? Okay, y is a dot x minus mx. All of them are vectors. This transform takes a vector x and converts it into a vector y, transferring from the first field to the next field, okay, from x to y. We will see why is y field, y space is better than x field or not, x space or not. We see that y is very better than x in some situations. We will see shortly that the new population of vectors y possesses a couple of very useful properties. Okay, that means y space is better than x space and is very good for, again, for compaction and again for comparison, okay, using KLT. Mean and covariance of the new population. We said about mean and covariance of X domain or X population, and we see mean and covariance of the new domain or new population. Okay, we can demonstrate very easily that MAY, mean of Y population, or expected value of Y is 0. Oh, this is the proof. EY. Using from the definition, what was Y? Y was a dot x minus mx. Okay, this is the KLT. EY is a dot m minus mx, or a is entering, e is entering, e or expected value x minus mx. Okay, or a dot eax minus max. Okay, we use this simplification using the ergodic principle. Okay, if our process wasn't ergodic, we couldn't use these simplifications. Okay, that's right. But EMAX is MAX for an ergodic process. Okay, and EAX is MAX. That means EAY or MAY is A EAX minus by EMAX. Okay, that means these are the same. EAX, okay, EAX is MAX and EMAX is again is MAX. This is wrong, not 0 minus 0. I draw here. This is wrong. This is MAX and this is M. Okay, MAX minus MAX. M minus M is 0 and A dot 0 is 0. Okay, that's right. Let us find the covariance. This was about the mean. we proved that mean of y is 0. What about the covariance? Or what about CY based to CAX? Let's find the covariance matrix of the population of y. You can demonstrate very easily that CY is A, CAX, AAT. Why? This is the proof. What is CY? CY is, by definition, EA, expected value of y minus MY dot y minus MY transpose. Okay, you know this item as X. CAX was EA x minus MAX dot x minus MAX transpose. CY is this item, but it is EA YY transform. Okay, why this item? Because here we proved that MY is 0. MY is 0. This is MY. Okay, this is 0. This is MY is 0. By here we proved it. Okay, this covariance means EA y minus 0 y minus 0 transpose. That means EA y transpose. But what is y? Y is A x minus MX. That means this is expected value of A x minus MX y transpose A x minus MX transpose. All of them transpose. Okay, here transposed. That's right. Is equal by expected value of this is itself A x minus MX. What was it? A parenthesis transform is parenthesis transform dot A transform. You know it. Okay, from algebra. A dot for example, A B transpose means B transpose A transpose, and here A parenthesis transpose is parenthesis transpose dot A transpose. That's right. Okay, A is outwarding from the expected value. Okay, and AAT is outwarded from expected value because it's independent of A. Okay, that means this is A EA x minus MX dot x minus MX transpose dot A transpose. That's right. What is it? EA x minus MX dot E minus x minus MX transpose. Its definition of covariance of X CAX. That's right. That means CY is A CAX AAT, and the proof finished. That's right. Therefore, CY A CAX A transpose proved, and is of dimension n by n as dimension CAX. CAX was n by n, CY is n by n. What is CY? CY is A CAX A transpose. What is it? Maybe we see in the next slides. Maybe CY is very better than CAX. Covariance function of matrix of the Y space is better than covariance matrix of the first space. Okay, we see here some discussions about covariance of new population Y domain or Y space. Let us further analyze the relationship CY A680. Suppose that the eigenvectors of matrix CAX are the column vectors E1, E2, En. Okay, these are the corresponding rows of CAX. Okay. We assume that the eigenvectors of the covariance matrix CAX of dimension n by n form an orthonormal set in the n-dimensional space. Okay, all of them are orthonormal to each other because of the eigenvector property. A transpose. Firstly, we calculate CX A transpose. Okay, means CX A transpose here E1, E2, En. That means CX E1, CX E2, and CX En. From the first definition of eigenvectors and eigenfunctions, okay, we had CXE is equal by lambda E. Okay, this definition of eigenfunction and eigenvalue and eigenvector. CXE is lambda E. Here CXE1 is equal by lambda 1 E1. CXE2 is equal by lambda 2 E2. Why? Because each of eigenvectors has a corresponding eigenvalue. E1 lambda 1, E2 lambda 2, etc. CX lambda 1 gives us lambda 1 E1. CX lambda E2 gave us lambda 2 E2, and etc. CX En lambda n here. That's right. This was CX AAT, but here CY A is A dot that component, A dot CX A transpose. What was A? A is E1 transform, E2 transform, etc. CX AAT we had in the last slide. Lambda 1 E1, lambda 2 E2, etc. Okay. Here, producing this vector to this vector, this item to this item, this item to this item, etc. But what about EI transform dot EJ? EI transform EJ. Using the property of orthogonality or orthonormality, okay, we know that EI transform EJ is zero for all of I and J's, and is 1 for only when I was equal by J. For example, E1 transpose E5 is 0. E2 transpose E3 is 0. But E2 transpose E2 is 1. E1 transpose E1 is 1. Okay? Only for I equal by J. Since the set of column vectors J or EI, I from A1 to N, consists a set of orthonormal eigenvectors. Using this property of orthonormal eigenvectors, we have this item, okay, of the covariance matrix Cx. And finally, from the above analysis, it's straightforward that this item, very important, Cy is all of items are 0 except in the main diagonal. Okay, here all items are 0, 0, 0, 0, 0, 0. All of them, these are zeros. Okay, and these are zeros. But here in the principal diagonal, we have lambda 1, lambda 2, lambda 3, lambda 4 to lambda n. That means we see in the last slides, Cy gives us better independency between the components of new population or Y population or Y space compared to X population or X space. More independency, okay? Oh. Why? Then I see my here I stop share my file and share my document for seeing the 11 slide. Okay, stop sharing, share my screen, share. Here you see this slide. This is the slide 11. Okay, this slide 10 we said about it, and this is slide 11. After this item we go back for better quality. That's right. I stop my camera for better quality. You see my screen. Observation regarding the new population Y domain. In this transformation, we started with vectors x and created vectors y. Okay, since both original and transform vectors, x vectors and y vectors, consist of values of n images. What do you say, Mrs. Dalal? Please, instead of yeah, please type Shift X. Instead of typing yeah, please press Shift X. I can't read these documents or comments. Please type again. Shift X instead of Y. Instead of yeah. That's right. Since both original and transform vectors consist of the vectors of n images at a specific location, for example, IOJ pixel, we see that starting from n images, we create n new images by assembling properly all the vectors of population Y. That's right. Looking at the form of Cy, we immediately see that the new images are decorrelated to each other. We said here, only this, no, only here, only over this main or principal diagonal we have non-zero components. Okay, this is for CFI, for covariance matrix. That means the new images or Y images are decorrelated, don't have any correlation with each other, or are independent of each other. That's right. Furthermore, since we said row 1 was eigenvectors with larger eigenvalue, and the final row or bottom row was the containing the eigenvector with the smallest eigenvalue. Okay, or here, since lambda 1 is greater than lambda 2, lambda 3, etc. to lambda n, we see that as the index of a new image increases, okay, from 1 to 2, from 2 to 3, increasing index, okay, its variance decreases. Okay. Why? Because we rearranged it firstly. That means the first image in the Y domain, okay, the first image or the first component is correspondent with the lambda 1, the larger item, okay, or the large variance, okay. The second row is for the second component and lower variance, and etc. The last row is correspondent to lambda n and smallest variance. This is this sentence. We see that as the index of a new image increases, its variance decreases. That's right. We call that from the form of CY. We see that the variance of image I in the new set is lambda I. We said lambda 1 is larger than lambda 2, etc. That means the first image or the first component in the Y domain has the largest variance, and the last component in the Y domain has the smallest variance. That's right. It's possible that a couple of the last images or small variance images, last images is small variance images, okay, in the new set or Y set have very small variance. They are almost constant images. We see in the next slides. In general, a signal with a small variance is a slowly varying signal. This type of signal does not offer any information, and we can easily delete it. Okay? And this is compacting the informations. We can discard the images which have low variance. Okay, that's right. Go to next slide. Here I stop my screen share and go to that form because of better quality. Stop sharing. LT here. This is the slide 12. That's right. We see that using KLT transform, we can convert the first and the original images to a new set of images, okay, and we can ignore the last images in the new domain, and we lost a small section of informations, okay. This is the goodness of the KLT transform. That's right. What about the inverse KL transform? To reconstruct the original vectors x from the transfer vectors y, we note that A inverse is A transform. That's right, because of orthogonality and orthonormality. Therefore, starting from the forward transform y equal A dot x minus max, by definition, we obtain that. We obtain the inverse KL transform as follows. Y is A x minus max. Okay. From it, A transpose Y is A transpose dot A is I, or identity matrix, or okay, or 1. A transpose Y is 1 dot x minus max, okay, or x minus max, and here max going to next side, x is A transpose Y plus by max. Reconstructing x from y. This is the inverse method. X is AT y plus by max. Okay, but when using y, when constructing y, we knew that could eliminate some vectors or some small variation images, okay, and here in reconstructing we have a new x, okay, a hat x that almostly is the original x, okay. Here we see these sentences. We know from a cropped matrix AAK of size chi by n, not n by n, k by n. For example, from 10 items, we had 10 original images. Image 1, image 2, x1, x2 to x10, okay? And we transferred it to the y domain, y1, y2 to y10. And we, for example, eliminated 7 items, 7 components in y domain, and selected only y1, y2, y3. Okay, this is AAK, k by n. Okay, a corrupted matrix AAK of size k by n, not n by n, using only the k eigenvectors of CX. The k largest value of eigenvalues, okay, of CX, which correspond to the k largest eigenvalues. That's it. The vectors of the new population of y are now of size k by n and are denoted by yk. Yk is a good approximation of y. Why? Because we selected the eigenvectors with largest eigenvalues. Okay? By using the inverse transform in the later case, or in yk case, okay, we obtain an approximation of the original vectors and therefore the original images as follows: x hat, a tablet for an approximation for x, for original x hat is AAK transpose, not A transpose. AAK transpose, some portion of AAK transpose dot YAK. YAK, what is YAK? For example, containing three components, Y1, Y2, Y3, not Y1, Y2, Y3, 2, Y10. Okay, YAK is a selection of all of Y's with largest eigen values. Okay, X hat is AAK transpose YAK plus by MAX. It says forward. And this is inversing KLT with some compaction and comparison. Okay, these components. Next slide. Mean squared error of approximate reconstruction. We had an approximation. Okay, for example, we converted from we transferred from X domain to Y domain. Then we neglected and deleted some components of Y. For example, we neglected in my speak 7 items from 10 items. Okay, in this slide we are speaking about the inserted error. Okay, how many error is inserted to Y domain and in transferring to X domain again in reconstructing. Mean squared error of approximation or approximate reconstruction, or X hat. It can be proven that the MSE or mean square error between the perfect reconstruction X, the original X, okay, X itself, and the approximate reconstruction X hat, approximately X, okay, is given by this expression. MSE mean square error is X minus X hat part by 2. That means sigma all of lambdas from 1 to n lambda j minus sigma selected lambdas. Okay, this is the selected and eliminated lambdas. No, this is error. This is all of lambdas, and this is selected lambdas. These are good lambdas, not eliminated lambdas. For example, these are lambda from 1 to 10, and these are from 1 to 3, for example. We eliminated or deleted lambda 4, 5, 6, 7, 8, 9, 10. Okay, that's right. Lambda j from 1 to n minus from 1 to k means sigma from k plus by 1 to n. For example, lambda, in my example, lambda 4 plus lambda 5 plus lambda 6, lambda 7, lambda 9, lambda 10. But don't worry, because these lambdas are small lambdas. Large lambdas are, for example, lambda 1, lambda 2, lambda 3. Other lambdas, lambda 4, lambda 6, lambda 10, are small values lambdas. Okay, small lambdas. And this is a small error. We see that the error is the sum of the eigenvalues or lambdas, eigenvalues whose eigenvectors we ignored in the vector reconstruction. For example, we ignored E4, E5, and etc. Okay, and this mean square error is sum of lambda 4, lambda 2, lambda 10. Go to next slide. To this slide, we see that, or we saw that this was a good transformation, because we went from the original space, X space, excuse me, my connection was lost, but I continue. Okay, I continue. We said this transform was a good transform, okay? But we have some drawbacks. Why? We see here. Despite its favorable theoretical properties, the KLT is not used in often practice for the following reasons. Okay, that means is some bad transform because these items. Its basis functions depends on the covariance matrix of the image CX. Okay, and hence they have to be computed and transmitted for every image. That means it's therefore what we call data dependent. Why? When you add some images, some new images, okay, you again should recalculate the CX. For example, we had 10 images from image 1 to image 10. And when we have the 11 image, again we should reconstruct and recalculate the CX, okay, and it is very time consuming. Another one, perfect decorrelation is not possible. We saw that we had only lambda CY was only non-zero over the principal diagonal, okay, but there isn't okay in the practices, okay. Perfect decorrelation is not possible. Since why? Since images can rarely be modeled and as realizations of ergodic fields, okay. We saw that if our images or random variables was an ergodic from an ergodic process, we should or we could, for example, tend to these results, okay. But our images aren't independent or aren't from independent sources, okay. That means they aren't ergodic processes or ergodic variables. That's right, and that tend to not perfect decorrelation. That's right, and not all of the KLT, for example, good properties. That's right. Another one. If we had independent images, this transform is very good. But if our images, for example, in a stream of video, if our images had some relations with each other or not independent, KLT don't work good. That's right. Or don't have perfect decorrelation between the images. Another one. I go here. Then next item here, the next item. There are no fast computational algorithms for its implementation. For example, we saw that in DFT, okay, we had FFT. In, for example, DWT, we had FWT. Fast, for example, Fourier transform, fast Hadamard transform, fast Walsh transform, okay? FWT means fast Walsh transform. When our components or samples were a power of 2 power by n, okay? But here in KLT, we don't have a fast protocol or fast algorithm. Another drawback. And the last item here, multiple realizations of an image are required. This is not always possible to achieve beforehand because we need why? Because we need calculating m or max for transferring in inverse. In inverse, we had, for example, x hat was c y y, okay, or here x hat was a at y a k or a at y plus by max. We need max, okay, and max means for calculating max or mean, we need a multiple realization of an image, and maybe in some situations this isn't achievable, okay, and this is the another drawback. Go to the next slide. In 4 slides we see some examples, and this is the end of our discussion about KLT and about all of transforms in our lectures, okay, but thus be patient to about 5 minutes, okay, less than 10 minutes. Example of KLT. These are original images. Image 1, 2, 3 from channels 1, 2, 3. For example, we said in multi-spectrum image parsing, okay? For example, channel 1 in this wavelength band, okay? For example, this micrometers to this micrometers. Channel 2, channel 3, etc. Okay? 6 spectral images from an airborne scanner. For example, from the sky, you are seeing the Earth by some different channels, okay, or different frequency bands. This is the image from channel 1, channel 2. This is X1 IOJ, okay, from 00 to NN. This is X1, this is X2, X3, X4, X5, and X6, okay, and all of them is a population of x's. That means x, total x, okay. Oh, again, stop sharing, and again share my screen. Here, this is the slide 16. These are principal components. These are Y's, okay. Here we saw x1, x2, x3, etc. These are y1, y2, y3, etc. This is y1, component 1, component 2, component 3 to component x in the y domain or y space, okay. But here you see, this is the component 1. Component 1 has this lambda, the largest lambda, okay, the largest eigenvalue. For example, 3000. component 2 have the next large lambda, for example about 1000. Other components, okay, 3 to 5 have a smaller lambdas, okay, 3000, 1000, 100, about 100, less than 100, 80, 60, and 13. Okay, these are very small lambdas compared to these two items, component 1 and component 2. And again, you see here we said components with large lambdas have large variations, okay, large variances or large variations. This is the larger variations, this is the next variations, and these items you don't see any variations, and these are for example large lambdas have large variations, okay, large variances or large variations. This is the larger variations, this is the next variations, and these items you don't see any variations, and these are for example as DC images, don't have any information in these items, and thus we can delete these 4 components and keep only these 2 components, okay, that tends to comparison. Okay, go to the next slide. Here all of them, these 6 items are the original images, image 1, 2, 3, 4, 5, 6, and these 6 items are the Y domain. These are X domain, and these 6 are Y domain. Okay, in the Y domain, for example, in this example, you see only these 2 items are okay, and these 4 items can be neglected or ignored or deleted. Okay, and go to the last slide. Another example, original image left and principal components right. For example, from a sky you have these 4 images in 4 channels, okay, and these are the Y space, these are X space, image 1, 2, 3, 4, and these are the transferred images or components in Y domain, component 1, 2, 3, 4. You see here the base component is this item, or maybe plus this item. These items are DC or have no variations, okay, and can be neglected with a good or a small error, a small mean square error. That's right. And this was the meaning of the last transform, KLT, Chronology Transform. Okay, I stop sharing, and this was I shared document for I see for the last session where I was here. Okay, this was the last transform we had in these sessions. From the start of the semester we had some principles, okay, principal items, some introduction, then we went to part 1. What was part 1? Part 1 was discussing about transforms, okay, unitary transforms. We started with Fourier transform. discrete Fourier transform. Then we went to cosine transform. I type here. We had firstly discrete Fourier transform. Okay. Then we DFT. Then we went to discrete cosine transform. Then we go for discrete Walsh transform. Okay. Then we go for discrete Hadamard transform. Here I type non-ordered and ordered. Okay, and we see ordered Hadamard. Okay, ordered Hadamard transform was good or is good. Okay, I type next. And lastly, we had Cronin-Leib transform or KLT. These items. We had Fourier transform, cosine transform, Walsh transform, Hadamard transform or ordered Hadamard transform, and lastly we have Cronin-Leib transform. This is the end of all transforms. Okay. In the next week we go, for example, for image enhancement. Okay, or about histograms and other items. That's right. If there's any question, I say you مع السلامة. خداحافظ شما.